In problem 2.5 on page 32, we are asked to say if the following statements are true or false. So all of these are conceptual questions. So the first one says the ground state energy of a particle in a box is 0. Ground state is 0 for a particle in a box. Now, we know that the energies of a particle in a box are given by n squared h squared divided by 8ml squared. And we know that n is equal to 1, 2, 3, and so on. So the energy is definitely quantized, and the value of n only starts from 1. So the ground state energy is going to be h squared over 8ml squared. And this is definitely not equal to 0 because none of these values are equal to 0. Right, so the ground state energy is never equal to 0. And in the text, it has been explained why n can never be equal to 0. The value of energy could potentially be 0 if n is 0, right? So when n is equal to 0, the energy is 0. However, the fact that energy is equal to 0 would mean that the wave function inside the box would have a value of something like, let's say it's b times sine to the power, sine of 2 pi over h times 2me so we have this on page 24, right? This is equation 2.17. So this is an equation that we have in the process of identifying what the wave function and what the energies are. So if the ground state energy were to be 0, then it would mean you have sine of 0, which is 0, right? So the wave function is going to be 0 for all values of x. So once the energy is 0, your wave function is 0, irrespective of what the value of x is. So even if x is between 0 and L, which is the length of the box, length of the one-dimensional box, the wave function in the box is 0, which indicates that you don't really have a particle there, right? But that is not true. We know that at some point in the one-dimensional box, for some value of x, the wave function should not be 0. The probability density and the probability should not be 0. You should be able to find the particle somewhere in the box. But the energy equals 0 ensures that you cannot find a particle anywhere inside the one-dimensional box. So the first statement is false. Now let's move on to part B. The particle in a box energy levels are equally spaced. Let's check this out. So the energy of, let's say, the nth level is given by n squared, h squared over 8ml squared. And the energy of n plus 1 level is given by n plus 1 squared times 8 squared over 8ml squared. Now, the question says that this energy difference is a constant for all n. So for any two energy levels, the difference in energies is the same, that they're equally spaced. We can compute this, right? So this would be equal to n squared plus 1 plus 2n times 8 squared over 8ml squared. minus n squared 8 squared over 8m l squared. Now I can write this as now I can basically cancel out the terms here, and the difference in energies is just L squared, right? And this value is not a constant. So if you were to look at the difference in energies, like between the first two states, here in this case, n is equal to 1, right? So that would be 3 8 squared times over 8 L squared. Now, however, let's say you want to look at the difference between the fifth and the fourth energy levels. They're also they're also like two immediate states, right? So if you were to look at their energy difference, that would be, here you have n is equal to 4. So 4 2s are 8 plus 1. I'm just going to write it as 9 8 squared over 8m L squared. So we see that every two energy levels are not spaced equally, right? The difference between two energy levels is clearly dependent on what energy level you're looking at. And you can actually see that the spacing, the difference in energies increases as n increases. So when you move to higher and higher states, the energies of those states are going to be farther and farther apart. So the answer for part B is false, because the energy levels are not equally spaced. Now moving on to part C. Increasing particle in a box stationary state energy corresponds to increasing the number of nodes in the wave function. This is a true statement, right? So the energy is given by this, and the wave function is given by n pi x over L, and in both the cases, n can be 1, 2, 3, and it can take any value, right? So when you're increasing the particle in a box stationary state energy, when you say energy is being increased, we know that it implies that the state itself is being, the state number is being increased, right? The only way the energy can increase is when you move to higher states, right? Because everything else in here, 8 square, 8m and L square, they're going to remain constant for a given length of a box, for a given mass of the particle, and Planck's constant is anyway a constant. So they're all going to stay constant. So the only way energy can increase is when the state itself, the state n itself increases. When you move towards higher states, you move towards higher energy. So an increase in the energy corresponds to increase in number of nodes. That is what the statement tells us. So in this particular wave function, when you have a node, the value of the wave function at the node is 0, right? So the wave function can be 0 only when sine of n pi x over L is equal to 0. We know that at x equals 0 and L, in both the cases, the sine value is going to be 0. You have nodes at the ends, but within the box, you have a node when this happens, when x is not equal to 0 or L. For a value of x that is not equal to 0 and L, you have a node inside the box. Now, when n is equal to 1, right? When n is equal to 1, you have over L. Now this can only be 0 if and only if x is equal to 0 or L. So you don't really have any nodes inside the box when n is equal to 1. Now when n is equal to 2, you have sine 2 pi x over L, right? Now this value can be 0 when x is equal to 0, when x is equal to L. These are the obvious choices, the ends of the box. But this can also be equal to 0 when x is equal to L by 2, right? When x is equal to L by 2, this becomes, I can cancel out the L, then I can also cancel out the 2. So this is just going to be, you are just going to have sine pi, which is 0, right? So there is one value of x inside the box that will make your wave function go to 0. So you have one node. When n is equal to 3, this is going to be sine 3 pi x over L. Now this can be 0 only when x is equal to L by 3. 0 and L are obvious choices, but x can be L by 3, but it can also be 2L over 3, right? So 3 pi times L over 3 like this, or 3 pi over L times 2L over 3. In either cases, I'm going to cancel out this, and this will give me either pi or 2 pi, and sine of both pi and 2 pi is 0, right? Now, at n is equal to n, sine n pi x over L. Right now, this can be 0 only when x is equal to 0, L, the obvious choices, or x is equal to L over n, 2L over n, and so on until n minus 1 times L over n, right? So when you have n is equal to 3, you had 2 nodes. When you have n is equal to, let's say, n, you're going to have n minus 1 number of nodes, because you can go all the way from L over n to n minus 1 over n times L, right? So these are 1, 2, 3, 4, and so on until n minus 1. So you have n minus 1 nodes. So with increasing energy, when you tend to access higher and higher states with increasing energy, with increasing n value, the number of nodes is also going to increase. So the answer for C is true. Now moving on to part D. Every solution of the particle in a box time-independent Schrodinger equation is an allowed stationary state wave function. The answer to this question is false. And that's because only wave functions, or like solutions that meet certain conditions, like being continuous, can be called, or can be allowed to be stationary state wave functions. In the case of a particle in a box, of course, the probability or the probability density is not going to change over time. So that's definitely a stationary value. However, the function itself needs to be continuous. And because that's not the case in all the solutions, the statement given in part D is false. So moving on to the last part, E, the PIB, the particle in a box transition that absorbs the photon of longest wavelength is from n is equal to 1 level to the n equals 2 level. So energy at n equals 1 is, call it, n square is 1, so h square over 8ml square. At n equals 2, it's going to be 4, n square is 4. Yeah. So the statement says that the transition that absorbs a photon of longest wavelength and energy of photon that absorbs this wavelength is given by hc over lambda. This is what we learned in chapter 1, which is also equal to h times nu when you use the frequency, right? So when you have this to be the longest wavelength, that would imply that the energy for the transition is going to be the smallest possible energy. The transition should have the smallest energy, right? Now, the transition energy for this is going to be 3 h squared over 8ml squared. And we have previously seen that the transition energy is 2n plus 1 times h squared over 8ml squared. Now, this energy is going to increase with n. As n increases, the difference in energy increases. So if you want to have the smallest, let's call it delta E, the smallest delta E, then you're going to have the smallest n, which is equal to 1. So the transition corresponding to n equals to 2 and n equals to 1 is going to have the smallest energy or the longest wavelength. So the statement in part E is actually true.